Picture the last moment of a star. It has burned for 10 million years. Hydrogen into helium, helium into carbon, carbon into oxygen, fusing heavier and heavier elements in nested shells like a cosmic onion, each layer burning hotter than the last. For 10 million years, it has held itself together through a perfect violent balance. The outward pressure of nuclear fire pushing against the inward crush of its own gravity. Then the iron core forms. Iron won't fuse. Iron absorbs energy instead of releasing it. And in less than a second, not a minute, not an hour, less than 1 single second, the core collapses. The outer layers fall inward at 1/4 the speed of light, slam into the newly collapsed core, and rebound in an explosion so violent it briefly outshines the entire galaxy it lives in. What's left behind is a point, a singularity, a place where our equations stop working and quietly display something that in mathematics means we give up. We call it a black hole. And for 50 years, we've told you the story of what it does. It destroys. It consumes. It erases. Matter falls in and ceases to exist. Information, the quantum fingerprint of every particle that ever crossed the event horizon, is gone, deleted. The universe forgets. That story is wrong. Not slightly wrong. Not wrong in a minor technical footnote that only matters to specialists. Wrong in a way that, if the correction is right, forces us to rebuild our understanding of reality from the ground up. Wrong in a way that even Stephen Hawking spent the last decades of his life trying to reconcile. And wrong in a way that the physics community has been quietly, furiously fighting over since 1974. Let's go back to the beginning. In 1974, Hawking did something that seemed impossible. He combined general relativity, Einstein's theory of gravity, the physics of the very large, with quantum mechanics, the physics of the very small. These two frameworks have never been fully unified. They operate by different rules, speak different mathematical languages, and when you force them together, they usually produce nonsense. But at the edge of a black hole, Hawking forced the conversation. And what he found shook the foundations of theoretical physics. Black holes aren't black. They glow, faintly, imperceptibly, but they radiate. Not from inside the event horizon, nothing escapes from inside, but from the boundary itself, through a quantum process now called Hawking radiation. Pairs of virtual particles constantly flicker into existence near the event horizon. Normally, they annihilate each other instantly. But at the edge of a black hole, one particle falls in while the other escapes. The black hole has to pay the energy bill. Over an incomprehensibly long time, it slowly loses mass. It evaporates. This was a stunning, beautiful result. It meant black holes weren't eternal. They had a lifespan. But then Hawking noticed something else. Something he initially dismissed and then couldn't stop thinking about. If the black hole evaporates, what happens to everything it swallowed? The radiation it emits is thermal, random. It carries no information about what fell in. A black hole that swallowed a library is indistinguishable from a black hole that swallowed a cloud of hydrogen. When it finishes evaporating, both leave behind the same featureless, random hiss of radiation. The library is gone, not transformed, not scattered, gone. This is called the black hole information paradox, and it is not a philosophical puzzle. It is a direct, irreconcilable contradiction between two of the most successful theories in the history of science. Quantum mechanics has a rule. It's not a suggestion, not an approximation, not a useful guideline. It is a foundational axiom of the entire framework. Information cannot be destroyed. The quantum state of a system evolves forward in time, and it can always, in principle, be run backward. The past is encoded in the present. Always. General relativity, applied to black holes, says information is destroyed. Completely and permanently. Both theories are among the most precisely tested frameworks humanity has ever constructed. Both can't be right. Both appear to be right. This is the crisis. and for 5 decades it has quietly sat at the center of theoretical physics like a splinter nobody can remove. Now here is where the public understanding completely breaks from the scientific reality. The story we tell about black holes, that they are the ultimate destroyers, the universe's trash compactors, the voids that consume and annihilate, is not just simplified. It is specifically wrong in the direction that the physics finds most disturbing. Because the leading solution to the information paradox, the one that the majority of theoretical physicists now tentatively accept, says something almost incomprehensible. Black holes don't destroy information. They encode it. On the surface. Literally on the surface of the event horizon, stretched across a 2-dimensional boundary, every piece of information about everything that ever fell in is preserved. Scrambled beyond any practical recovery, but preserved. The 3-dimensional interior, the singularity, the drama of objects falling in and being crushed, all of it may be a kind of projection. A hologram cast by the 2-dimensional data written on the horizon's surface. This is the holographic principle. And if it's correct, then the thing we've been calling a destroyer is actually the most perfect information storage system in the universe. That's the first unsettling reversal. Here is the second. We don't know if the singularity is real. The singularity, that point of infinite density at the center of a black hole, is where general relativity breaks down. Physicists are broadly agreed that infinite density is not physically real. It's a symptom of an incomplete theory. The same way dividing by 0 doesn't give you infinity in nature, it gives you a sign that your equation has stopped describing reality. String theory proposes that the singularity is replaced by a tightly wound structure of strings at the Planck scale. Loop quantum gravity proposes a quantum bounce, a region of extreme but finite density where space-time itself becomes grainy and discrete. The firewall hypothesis, proposed in 2012, suggests something even stranger, that the event horizon itself is not the smooth, crossable boundary general relativity describes, but a wall of Planck-scale energy that incinerates anything attempting to cross it. That last proposal nearly caused a civil war in theoretical physics. Because the firewall directly contradicts Einstein's equivalence principle, the foundational idea that falling freely through curved spacetime should feel locally identical to floating in empty space. If there's a firewall, an astronaut falling into a black hole doesn't experience a peaceful crossing of the event horizon. They're incinerated at the boundary. The gentle tidal stretching we describe in textbooks, what physicists poetically call spaghettification, may be irrelevant. You'd never reach it. The community has not resolved this. A decade of work produced counter-proposals, modifications, and partial reconciliations, but no consensus. The interior of a black hole remains, in a very precise sense, theoretically disputed territory. We have imaged a black hole. 2 of them. The Event Horizon Telescope captured the shadow of M87 in 2019 and Sagittarius A in 2022. These are real objects, observed directly. The event horizon is not metaphor, and yet we do not know what happens at the boundary. We do not know what, if anything, exists inside. We do not know whether information survives, and if so, how. We do not know if singularities are real or mathematical ghosts. We have 4 competing frameworks: general relativity, string theory, loop quantum gravity, and quantum information theory, that each partially describe black holes and fully agree with none of the others. The images are real. The physics behind them is in crisis. Here is what the crisis means in plain language. Every confident claim you've absorbed about black holes, the dramatic visualizations, the descriptions of event horizons as points of no return, the narrative of ultimate destruction, is based on general relativity applied to regions where general relativity openly admits it doesn't work. We are using a theory past the edge of its own validity and presenting the results as settled science. Black holes are real. Their gravity is real. Their event horizons are real. Everything else, the interior, the singularity, the fate of information, is a question mark wearing the costume of an answer. The most dramatic objects in the universe are also the least understood. Not around the edges of our knowledge, not in some obscure corner of the parameter space. At their literal center, we photographed the shadow and called it understanding. We named the darkness and called it explained. The universe did not agree.